Good evening, everyone. Welcome to this tutorial session on discrete mathematics. Today we'll be discussing week 11 questions from previous iteration of this course, and our focus of our discussion would be recurrence relationships. So I'll start by sharing my screen. I hope the screen is visible to everyone. So let's get started with the first question. So, which of the following is true in the context of an n-bit string? So, what the context is basically is in how many ways a binary n-bit string can be formed. So, for example, if n equal to 4, say, so example would be 1101. So you have 4 bits. Each digit represents a bit. So in decimal system we call it digit. In binary system we call it bit. This is a valid example. So it could be something like 010. This is both are valid expression. So the question is, in how many ways n-bit string can be formed? So how to do it is basically we consider an n-bit. So let's say this is an n-bit string. Let me divide it. This is n-bit string. So l- let us say that we can form tn uh, binary strings with n. We can form tn binary strings given n bits. So we can form tn binary strings with n bits. So this can be broken down into, if we consider the n minus 1 bits and the, so this is your n minus 1 bit string. And in this last bit we can place, we have two options, 0 or 1. So the recurrence relationships become tn, that is the total number of binary strings we can form, is tn minus 1, that is leaving one of the bits we form tn minus 1, and for every tn minus 1 we have 2. 2 because of the two choices 0 and 1. So tn uh, becomes 2 times tn minus 1. So given these options, if you see option B and option C are the correct answer for this question. So here in this question, they haven't asked for any constraint on the n bit string. So another popular question is if there was a if no two zeros can be placed con consecutively. So examples like 1 1 0 0 1. So this is not allowed, or 1 0 0 1 1. This is also not allowed. So things like this are not allowed. So in that case, how it will be? So just consider the n bit string again. So this is n bit. Now, if we place a 0 at the end, then we cannot place a 0 at the second last. We have to place a 1. So in which case that 1 has to be fixed. So we lock the position of 1. So we'll have to consider uh, n minus 2, a bit, the string of n with n minus 2 bits. Now, if I take the same s- case, and if I uh, let's say if I have 1 in the last bit, then there is no constraint on what I place it. I can play in the second last, so it can, there is no restriction in the consecutive one, so it can be 1 or 0 both. So in that case we can select n minus 1 bit. So this green one is n minus 1 bit. So basically, uh, t of n would become, in which case, if it is tn minus 2 plus tn minus 1, which is if uh, last uh, bit equals 0, if last bit equals 1. Last bit is the bit we are inserting, we are controlling the values either 0 and 1, and then we are, by the recurrence relationship, we are finding t of n. So this is basically nothing but a Fibonacci series. Fibonacci sequence. So if such a constraint is given, then it would be a Fibonacci sequence, and if it is not given, it would basically be 2 to the power n. So keep this in mind. This is not part of the question, but I thought for completeness sake I'll discuss. Okay, uh, coming on to the next question. So the solution of the recurrence relation an equal to an minus 1 plus 2 with initial term a0 equal to 2. So first what we do is write an equals an minus 1 plus 2. Again we can expand an as an minus 2 plus 2 plus 2. So again we can write an minus 3 plus 2 plus, if we add this to, it is 4. So it is basically an minus 3 plus 6. So if we write an minus 4, it would be 8. So in general, it is an minus k plus uh, 2k. So we have to go to 0. So n minus k, when n minus k is 0, k equal to n. So an would be a0 plus 2n, and a0 is 2. 2 plus 2n, which is nothing but 2 into 1 plus n. So therefore, option D is the right answer for this question. It is a pretty straightforward question. I hope it is clear. Coming to the next question, which of the following does not have the complexity of n log n? So in order, in the complexity uh, comparisons, so first comes constant, that is O of 1. So O of 1, it is like this. So you have a smaller set, which is O of 1. O of 1 is contained in another set. That set is O of n. Wait, just that is O of log n. So log n is less than n. Next, we have which is O of n, beyond which that is O of n log n, and even beyond that uh, would be, yeah, O of n square. Now if you see that which of the following does not have the complexity of n log n. So n log n is the graph of n log n. If you plot, it is more, it is above n. So anything with adding n to an n log n would remain some log n. So it is this one, the complexity is O of n log n itself. The second is you have this n and you have n square. So in n square, this 2 will come in front. It would basically be uh, this term would become 24 log n. So again, both n and log n are uh, this is n log n. This is n, and log n is somewhere here. Log n. So both of them, log n and n, are below n log n. So the complexity of this will also be n log n. Coming to the third one, n log n plus n square. Now n square grows faster than n log n. So this would, n square would dominate this complexity. So it would eventually be O of n square, and n log n plus 1000 log n, again this would be n log n. So the right answer is, so all of them will have complexity n log n except option C. So it would be O of n square. So option C is the right answer for this question. I hope that is clear. Okay. Moving on to question number 4. What is the solution of the recurrence relationship? So you have been given a linear recurrence relationship. So and initial condition a naught equal to 1 and a1 equal to 0. So what is the relationship? So you have an equal to 5 an minus 1 minus 6 an minus 2. For linear recurrence relationships, the way to do it is we assume that uh, we rewrite it like this: an minus 5 an minus 1 plus 6 an minus 2 equal to 0. We next we consider that let an minus 2 a okay, so let us an minus 2 is some alpha, an minus 1 is alpha times some lambda, and a n minus 2, sorry, a n would be alpha times lambda square. Now if we plug this in this equation, what happens is that we get alpha times lambda square minus 5 lambda plus 6 equals to 0. So that gives us lambda minus 3 and lambda minus 2 equal to 0. So actually, wait. The we assume this relationship, not this one. So write it like this. We assume uh, an as some lambda times an minus 1. Oh, okay. Now, uh, by this relationship, uh, this is equal to lambda times lambda square an minus 2. So what we pull out from when we substitute an minus 2, so it's we assume an minus 2 is non-zero, and we remove an minus 2 from both sides, so we get this lambda. So lambda can be 2 or 3, two different. So now the since it this expression is linear, so we can so any lambda 1, and so we call, let's say this is lambda 1 and this is lambda 2. So by this logic, it would mean it is lambda to the power n some a a0. So if we plug in, so if an equal to lambda to the power n, lambda 1 to the power n, some a0 would satisfy this condition. Also an equal to lambda 2 to the power n and some a0 would also satisfy this condition. So since this is a linear expression, so I'll write it like this. So what I mean is that lambda 1 to the power n a naught minus 5 uh, lambda to the power n minus 1 a naught plus 6 lambda n minus 2 A naught, that would be 0. Because why this equation holds? Because I can pull out A naught and lambda n minus 2. We'll get lambda 1 whole square minus 5 A naught into, sorry, 5 lambda 1 and plus 6 equal to 0. And since lambda 1 is the root of uh, this equation over here, so this would also be equal to 0, and therefore this equation holds true, and same goes for lambda 2 as well. So we have, let me pull it down. So we have some lambda n A naught minus 5 lambda n minus 1 A naught plus 6 lambda n minus 2 A naught equal to 0. And similarly, we have for lambda 2 also, lambda 2 to the power n A naught plus 5 lambda 2 to the power n minus 1 A naught plus 6 lambda 2 to the power n minus 2 A naught. Both these equations will hold true because lambda 1 and lambda 2 are roots of that equation. So now if I substitute some, if I add this, if I multiply this equation by some constant alpha 1. So if you see this equation, this A naught terms, this is basically a constant. And similarly here also it is a constant. So if I assume an, just like we did here, that an, so instead of A naught I call it some alpha 1, alpha times lambda to the power n. So what would happen is we can, this solution alpha 1 lambda 1 to the power n plus alpha 2 lambda 2 to the power n will also satisfy a n equals to 5 a n minus 1 uh, plus minus 6 a n minus 2. So this is the general expression for general expression for an. So this only holds for if the recurrence relationship is linear. So now what we'll do is we know lambda 1 and lambda 2. So lambda 1 was 2 and lambda 2 was 3. So basically an is alpha 1 2 to the power n plus alpha 2 3 to the power n. Now in the question it is given that a0 is 1 and a1 is 0. So it is like this. So a0 is 1 and a1 is 0. So now if I plug it here, a0 would be alpha 1 plus alpha 2, that is 1, sorry. And a1 would be 2 alpha 1 plus 3 alpha 2, that is going to be 0. So from this we get alpha 2 equal to minus alpha 1, and if I plug it in this equation, it's 2 alpha 1 minus 3 alpha 1 equal to 0, and so minus It just 1 minute. Mm, We get sorry. This is I 1 minus alpha 1. So if I substitute it here, it would be plus P minus 3 alpha 1. So it is 3 minus alpha 1 equal to 0, or alpha 1 is equal to 3, and alpha 2 we can get is 1 minus 2, that 1 minus 3, that is minus 2. So our an would become 3 into 2 to the power n minus 2 into 3 to the power n. So this is the expression for a of n. So the right answer would be option B. Note that this proof holds only if it is linear. Next question. Which of the following is a solution uh, to the recurrence relation an equal to an minus 1 plus n, where n is greater than equal to 1 and a0 is 5. So we have an as n plus an minus 1. We can split an as n minus 1 plus an minus 2. Similarly, we can split an minus 1 plus n minus 2 plus an minus 3. So it is basically uh, how many n. So if we go to, so it will be n plus n minus 1 up till n minus k minus 1 plus n minus k. Now we have to go to 0. So n minus k is 0. So n, so k equal to n. So this becomes n plus n minus 1 to 1. If we put k equal to n, this becomes 1 plus a0. This term we all are familiar with. It is n into n plus 1 by 2 plus 5. A0 is 5. That is given. So on rearranging, it is becoming 10 plus n into n plus 1 over 2. So the right answer is option B, n in 10 plus n into n plus 1 whole divided by 2. I hope this was clear. Moving on to the next question. So which of the following sequence is correct? So for this again, we'll is so we will draw like this. So this is your n log n. This n log n, and this is n square. So n squared is the biggest term. So now which option captures it? You see that 2 log of n squared is basically 2 log n. So log of n square is 2 log n, which is the of the same complexity as log n, and n is greater than log n square, and n log n is greater than n, and n square is greater than n log n. So option D is the one that correctly captures it. So in here, the problem in option A, the problem happens when we say this, where n square is less than log n. In n log n, here the problem occurs, and also uh, in option C, the problem occurs over here. These expressions are not correct. So other than that, only option D captures the inequality correctly. Moving on to question 7, which of the following is the correct recurrence relationship for climbing 99 stairs? Stairs simply means walking on stair, covering one or two steps, two stairs in one step. So suppose you have cover AN is number of ways to climb n steps. So for this can be broken down as you climb n minus one step, then take one step. This is uh, one way, and there are another way, that is an minus 2. You climb n minus 2 step, and uh, then take two steps. So these are the combinations in which AN captures the combinations in which you can climb. So to make it easier, I'll give an example with, let's say you have three steps. So you have n equal to 3. So AN would basically consist of all the combinations. So you have 1, 1, 1. You take one step, you take one step, and you take one step. That is 3. For you can have like this, you have 1, you take two step and you reach. You could have 2 and 1. So these are the ways in for n equal to 3. So for the number of such combinations is an. So in case of uh, n steps, what we do is we break the steps into n minus 1 and one more step. So is the is all the combinations in which you can reach n minus 1 steps, and then just one more step. So in all those, these are combinations. So these are all combinations. So for this an minus 1, you have certain combination, and you then add a 1 at the end. So that would make another combination. For this an minus 2, you have some combination, but at the end you add 2. So those make another combination. So basically an equal to an minus 1 plus an minus 2. This is also again Fibonacci series. So climbing n steps can also result in a Fibonacci sequence. And therefore, if you look at this options carefully, so you have option A as the right answer. Okay, coming to the eighth question. So which of the following statements is or are true regarding the sequence 0 to 6, 12? So if you notice, this is, let's say, uh, A0, A1, and so on. So between, so you have 0 to 6, 12, 20, 30, okay, 42, and so on. So A0, A1, A2, A3, A4, A5, A6. You see A1 minus A0 is 2. A2 minus A1 is 4. A3 minus A2 is equal to 6. A4 minus A3 is 8. A5 minus A4 is 10. And A6 minus A5 is 12. And it continues. So if you look at this number, so if 2 is equal to n, if we are denoting this, if we denote the first number as n, then this one becomes n minus 1, and this term is twice of n. That is valid for all the options. So we have an minus 1 is 2n. So this is one valid answer. And if we sum them up, so it would basically be an minus a0, and the sum would be sum of 2n plus 2 of n minus 1 up to 2 of 1. So we pull the 2 outside, and it would be n into n plus 1 over 2, that is uh, n into n plus 1. So option B and option C are both correct answers for this question. I hope that is clear. Okay. Uh, Coming to the next question. So which of the following are true? So n cube grows faster than n square. That is pretty simple. The solution of the tower of Hanoi has a complexity of 2 to the power n minus 1. This is also true. 8 log n grows faster than 4n. So log n always actually grows slower than n. So initially it may be that 8 log n is more than n, but eventually 4n will overtake 8 log n. So this is not right. So option 1 and 2 are the only correct answers for this question. Coming to the final questions for our discussion. So we have a recurrence relation an plus 5n plus an minus 1, and starting with a1 equal to 4. So what is the value of a20? So you have an equal to 5n plus an minus 1, um, and a1 is equal to 4. So uh, what is the value of a20? So we can expand an minus 1 again. So it would be 5 times n minus 1 plus an minus 2. This would be 5n plus 5n minus 1. Again, we can expand n minus 2, and so on. So this plus uh, we have sorry, plus an minus 2. So this would basically be 5 times n plus n minus 1 plus uh, n minus k up to uh, a n minus k. So we'll have to go to 1. So n minus k is 1. So k is equal to n minus 1. So an becomes 5 of n plus n minus 1 plus n minus n minus 1 plus a1. So this would be 5 into n plus 1 over 2 plus 4. So, and we have to find 20. So if I put uh, 20 over here, so let's see. Sorry. So I made a mistake over here. So it would be n minus 3, and this would be n minus k plus 1. So n minus k plus 1 is 1. So k is n minus 2. So it would go up to n minus 2. So mm, now we have n plus n minus 1, n minus 2 up to 2, and we have a1 which is 4. Now 4, we can write 4 as 5 minus 1. So that makes us include this 5 in this bracket itself. So it would be n plus n minus 1 plus n minus 2, 2 plus 1 and minus 1. So that makes it 5 into n plus 1 over 2 minus 1. And now we'll have to find, this is a of n. So a of 20 would be 5 into 20 into 21 by 2 minus 1. So that is 1050 minus 1, that is 1049. So the right answer is option C. So option C is the right answer for this question. So that brings us to the end of our discussions on recurrence relations. So if anyone has any doubt, you can ask. If you have any doubt regarding any question I have discussed or regarding the lecture notes, you can ask. All right, if no one has any questions, we can close the session for today, and we'll be meeting again next week at the same time. So thank you for joining.